All right, well, I'd like to thank everybody for their attention this afternoon. What we'd like to talk about today is things that you can consider in your groundwater monitoring plan around CCR disposal units, particularly those that are in corrective action, to make your groundwater monitoring program more efficient. The talk itself is organized into three pieces, and that's on the right of this slide. The first is a survey that's going to talk in general about the issues at play in understanding groundwater geochemistry and how it interacts with your monitoring program. We have some specific examples from CCR sites that have had issues that we've done some detective work with and that have led to an increased understanding of the groundwater geochemistry and the fate and transport of metals. And then the third section is a summary and conclusion. The basic issues here arises from the fact that there's national guidance for monitoring CCR units, and it's developed by the United States EPA, Environmental Protection Agency. And the fundamental issue is that that's national guidance, it's fairly general, and we have to deal with things on a very site-specific basis. So there's three things that go on to make this a difficult problem. The first is a classic interwell model, where you have groundwater background up gradient from the CCR unit. Then it travels underneath the CCR unit. And then in the downgradient side, you have your detection monitoring wells. And the idea is that any difference between the up gradient and the downgradient wells is added from the CCR unit. And so that's the kind of strategy you have. The problem is that classic interwell model often isn't valid at specific sites for a variety of reasons that we'll go into. The second issue is that the list of chemical of potential concern in Appendix 3 and Appendix 4 are put together not for understanding what's going on, but they're put together to kind of serve as an alarm system. So if you see increases in these chemicals, then it triggers a new phase of monitoring. And the other third issue with this is that these chemicals that are in Appendix 3 and 4 are metals and cations and anions that occur naturally. And so the alarm system itself can generate, and is in fact statistically is designed to generate false alarms, false positives. So in order to keep the false positives from triggering bigger issues, we can use some strategies from geochemistry to understand what's going on. A snapshot survey of groundwater issues in play across the United States. The first column shows EPA regions, which is how we chose to aggregate these. The second column shows the total number of CCR units that we were able to get reasonably ascertainable data for, a snapshot. And then the third column shows how many of those are in routine detection monitoring. And the fourth shows how are in other monitoring status, maybe assessment monitoring or corrective action. And this is a little bit fuzzy because some of the sites have state leads and they use slightly different terminology. But the important point is to understand that in that fourth column, there's a pretty significant number of sites where there has been an issue. The alarm system has gone off in the groundwater geochemistry. And this is not a rare event. It does not necessarily mean that the regulated CCR unit is the issue, but it means that further investigation and detective work is warranted. On the right-hand side of this slide, you can see a list of chemicals of potential concern. The ones that we've bolded are the ones that show up like a lot, maybe 10 times as much as some of the others. Those are lithium, arsenic, cobalt, and molybdenum. And these are pretty common. This is not a rare event. And the geochemistry of the chemicals of potential concern is important to understand at these sites. So what about some of the chemicals that we, the metals and the cations and anions that we look at? They have different chemical behaviors. Some of them are pH sensitive. That pH is a measure of the acidity in the groundwater. And the ones that say strong, that means that the way they interact with solids and surfaces in the subsurface and their solubilities are highly variable with pH. What about ORP? That's oxidation reduction potential. That says that the element can exist in one or more oxidation states. And the ones that say strong means its behavior is complicated depending on the oxidation state of the solution and the minerals that the groundwater might be passing through. Complexants, that's chemicals that interact with other chemicals in the water. And again, the behavior can be complicated or it can be relatively simple. Solubility controls are minerals in the subsurface that either can release chemicals into the groundwater, or if the concentration in the groundwater is high enough, it can cause precipitation. And then Zorber asks whether or not these chemicals can interact with surfaces of minerals and adsorb onto the surfaces. The final column talks about naturally occurring. Do these occur in nature as well as if there were no CCR unit at all? Could you find these in variable concentrations? And the answer in a lot of cases is yes. These do occur in nature. They're not necessarily, finding them in your groundwater is not necessarily indicative that there's a problem with your regulated CCR unit, but we have to understand this problem called background. The ones that are colored in red are the ones where this detective work, red or orange, can be relatively helpful. And the ones that are in yellow, the geochemical behavior is more simple, less complex, and you may have to look at other things or focus on other things when you're doing your detective work. The hydrogeologic setting also has a lot to do with it. These regulated units may be in glacial tills that are highly variable over a relatively small scale, or in river channel deposits. And the color scheme here is trying to indicate how much complexity the hydrogeologic setting itself has on understanding what's going on, both in terms of geochemistry and in terms of flow. The red ones are more difficult to deal with, and the orange are intermediate, and the yellow are relatively easy to deal with. You can see that a lot of the hydrogeologic settings that these CCR units are in have one or more characteristics that are fairly difficult to deal with. Okay, so how do we go about understanding what methods do we use to look at this? Well, if you just look at Appendix 3 or Appendix 4 list, you don't get a complete picture about the geochemistry of the dissolved constituents in the groundwater itself. So one of the things you can do is measure the concentrations of the major cations and anions and look at their ratios or their concentrations. And you can understand the origins of these of these chemical assemblages. And sometimes you can determine whether or not they come from the CCR unit itself or whether they come from someplace else, depending on whether, for example, on the right-hand side, this groundwater labeled C1 looks kind of the same as C2 and kind of the same as AH3. Those are three different wells. They have the general same pattern of major cations and anions, but somewhat different in composition. In this triangular and diamond-shaped diagrams, it's also separating things out relative to their origin and trying to show whether the red dots are the same or different than the blue dots. So the idea is that looking at the major cations and anions, as well as some of the Appendix 3 and 4, can help separate the origin of the groundwater geochemical assemblages. Another investigative methodology we can use is the sensitivity of different metals, major, minor, and trace cations to oxidation state. This tells how oxidized or reduced the groundwater is. On the graph on the right-hand side, the bottom axis is pH, and the vertical axis is the oxidation potential in millivolts. And this is for iron. And iron can exist in groundwater in two different states, iron 2+ and iron 3+. And this is a predominance diagram that shows what the dominant aqueous species are or solid species are as a function of pH and EH. And so you can measure the ORP in the field, which is not on the Appendix 3 or 4 list, and then you can look and see what oxidation states that your redox sensitive diagrams. There are many, many of these diagrams for molybdenum, for arsenic, and so on. And you can determine what different species ought to be predominant. And then from that, by knowing the fate and transport parameters of those certain species, you can make deductions about where they likely came from and where they're likely going to go. So this is what we call understanding the mobility of the dissolved constituents and how strongly it's affected by oxidation reduction potential. A third thing you can look at is geochemical speciation. This shows pH on the x-axis, and it shows percent of a metal carbonate species on the y-axis. And so the blue diamond shows at low pH, the metal is predominant. The red dashed curve line shows at intermediate pH, a bicarbonate species is predominant. And the beige colored dashes show that at high pHs, the carbonate species is predominant. These all have different solubilities and different degrees of adsorbing onto surfaces. And because the pH can be measured in the field, and you can go ahead and use a geochemical speciation code to understand what's predominant, you can also help understand the mobility of the dissolved constituents, where your groundwater has come from and where it might be going. And then the last investigative methodology we use is chemical fingerprinting. So what we want to know is whether or not there's chromatographic separation going on as groundwater moves downstream. So on the extreme right-hand side, what we see here is a graph that shows the composition of different cations and anions in groundwater at two different wells. One is near the source and one is downstream. And because they have the same general shape, just different sizes, we can deduce that there isn't really any differential separation along the flow path and that they might have a common source chemistry. And so this can be compared with the graph in the center, where the upgradient or the well near the source has a completely different shape. And this either shows that there's differential separation because of geochemical processes going on. Also, it can show that there's two different major element source chemistries. And perhaps if you bolster this with other arguments, that maybe your regulated unit is not what's causing these apparent exceedances in your downgradient wells. It can help you tell whether the plume is changing as it's going downstream or whether there's even a plume at all that's originating at a source. Okay, at this point, I hope I've given you a really quick and brief introduction to some of the methodologies and the issues at hand, and shown that they're relevant to a lot of sites across the United States. So what we want to do next is provide some very specific examples of the use of these methods and how they can solve specific permitting problems. And the guidance itself, as I hinted at earlier, emphasizes the need for studies that directly demonstrate the occurrence of a particular natural attenuation process or some other process at the site. And so we have to be able to demonstrate in our permitting process exactly what's going on by measuring things in the chemistry and tying them back to geochemical mechanisms. At this point, I'd like to turn over the floor to my colleague, Bernd Rehm, who's going to talk about the site-specific examples.
So one of the things that we look at is this whole question of what's actually dissolved and what's carried along as suspended solids. When things are moving as suspended solids, they're generally not reactive, and they may simply be a function of well development. That series of pictures in the upper right corner shows water from a single monitoring well that was pumped over time And each of those containers represents an equilibrium condition where you're measuring the field parameters, and the field parameters have stabilized, and you get your sample. But it turns out if you keep pumping, water quality gets better and better, to the solids go down. Typically, you're measuring turbidity as your key indicator of the suspended solids, and this little plot down in the center is showing that at turbidity levels on the order of 1 to 100 NTUs, you can have hundreds of milligrams per liter of suspended solids. So if you have a trace element, such as cobalt, on that suspended solid, and you're not filtering the samples in the field, which is a common practice under the CCR sampling, and then you dissolve that suspended material with the acid you use to preserve the sample, you release that metal. And that could give you very misleading results as to what you think is actually going on chemically. And this is very element specific. And so here we're looking at cobalt. And this is coming from a real site. And what you see here is turbidity plotted, or total cobalt plotted against turbidity. And you see a clear trend of increasing cobalt concentrations in unfiltered samples as the turbidity increases. And sure enough, you get the turbidity high enough and you trip across the site's groundwater protection standard. So now you have these turbid samples, not very turbid, you're talking about 30 or 40 NTU, you have these turbid samples that are creating a problem. The blue arrows indicate a couple of wells where an earlier sample that had met the stabilization criteria had relatively high turbidity, but a later sample came back with much lower turbidity, and you can see in this case, these wells were not in areas where you're talking about cobalt. In fact, these are deeper aquifer wells. So in the deeper aquifer, you see no relationship between the turbidity and the cobalt, but that's due to the stratigraphic setting of where the wells are. So you have to parse through the data fairly carefully to make sure you're looking at the right information. So the question is, what's going on? You want to demonstrate the mechanisms. So here we look at one step closer. We look at the sediment cobalt content and the sediment's iron content. One of the things that cobalt does, it adsorbs readily to iron oxyhydroxides. So here we're looking at this and saying, well, sure enough, the higher the iron content, the higher the cobalt content. There's a clear relationship between the two. So we're starting to identify a mechanism of what's driving the suspended sediment issue. So now you can go one step further and keep diving down. And now we're starting to look at what is this adsorptive process. And so here we're looking at a series of tests that were run to develop linear isotherms, or KDs, for the cobalt on the sediment in this particular site. So now we are clearly demonstrating a mechanism of adsorption. It's a linear adsorption over a range of aqueous concentrations that are relevant to our site. And just as importantly, we can ask the next question. So once adsorbed, is that permanent? So you can take these samples that have had cobalt adsorbed to them and then desorb them in cobalt-free water. And you find that 95% of the cobalt is irreversibly adsorbed to these sediments. So once it's tied to the sediment, it's pretty well fixed to the sediment. And the question of whether it's then chemically reactive or transportable as suspended sediment in the aquifer becomes of relevant issue to be considered in fate and transport analyses and potential release of the cobalt from a particular unit. You mentioned the fact that it doesn't work for all elements. Here's another site where we're looking at turbidity and lithium, turbidity and molybdenum, and there's no clear trend. So on these two particular elements at this site, there's no association between these elements and the suspended solids. So this question of suspended solids isn't always relevant, but for certain elements, certain COPCs, it can be very relevant. I'm going to switch to arsenic now. So we've got this site, and you can see the little sketch in the bottom. We have an upper pond that is the subject of the corrective action, and a former lower pond that has been taken out of service many years ago. Groundwater is flowing from the direction of upper pond to lower pond. We start seeing that monitoring wells that are down gradient of the former pond are high in arsenic and well above the arsenic groundwater protection standard. So now we start looking at the rest of the wells. You look at the bottom right, background and deeper groundwater. And by deeper groundwater, we're looking at deeper parts of the flow system that we don't believe are at all affected by the shallow groundwater flow associated with the regulated units. And you see there, it's aerobic, very low arsenic concentrations. And then we look at those monitoring wells that are down gradient of the upper pond. And you see a long range or a wide range of ORP. Some of them get very negative, but even the negative ones don't have arsenic in it. So all we're seeing is arsenic associated with that shallow groundwater down gradient to the former pond. So what's going on here? So now we're going to look at iron. And keep in mind, iron is not one of those standard Appendix 3, Appendix 4 metals, so it's done in addition to. What we start to see is that as the ORP goes down, especially in the area down gradient of the former pond, the iron concentrations climb very dramatically. And when you look at iron and arsenic, they're also related. High iron means high arsenic. So what's happening here? When we look at the materials down gradient to that former pond, we believe what we're seeing is arsenic release from iron oxyhydroxides that are dissolving as a result of a low ORP that's caused by the organic rich sediments that are present immediately beneath and down gradient of that lower pond. The lower pond was built a long time ago. We think what's happening is that the organic materials were used to form the berms of that lower pond. And that's what generates that low ORP, that generates the dissolution of the iron oxyhydroxides, that releases the arsenic. It has nothing to do with the unit currently being evaluated. So there's some examples. And what would like you to walk away from this presentation with is several key points. You need to address multiple constituents. You need to address the hydrogeology. The hydrogeology and the geochemistry go together. That the fate and transport of a number of elements of concern are controlled by one or more geochemical processes: precipitation, solubility, complexation, and adsorption. Controlling factors, pH, ORP, which drive the valence state of a lot of our constituents of concern. The counter ions, what else is in solution? Do you have iron present? Do you have manganese present? Are there suspended solids in the water that are controlling the apparent concentrations when you start to acidify unfiltered samples. This isn't the same across all elements. So you have to think about what is driving your particular concern on your site. You know, barium, fluoride, lithium, and molybdenum have weaker controls. Arsenic, cad, cobalt, chromium have stronger controls. And it's important that you understand the underlying processes. The EPA has made it very clear that if you're looking at things like monitored natural attenuation, if you're looking at alternate sources, you have to understand what the process is that's driving that conclusion. This requires site-specific testing that's beyond the minimum CCR parameter lists. We have some recommendations. Appendix 3 and 4 do not contain everything you need to figure out what's going on a site, or potentially to treat the exceedances in groundwater if you're moving to corrective action. You have field measurements that can help you evaluate what's going on. These field measurements are almost always collected as part of the stabilization process during sample collection, and then they get put into an appendix maybe and never looked at again. But they actually help you understand what's going on with many of these redox sensitive constituents and with other elements like iron that may have a significant control on the constituents of concern. You know, looking at major cations and anions help you with the origins of the aqueous constituents. Some of these are included in the lists, but they're not all present. So it's important to think about potentially adding a few additional analytes to the testing program. And that includes these key trace metals that may control the aqueous fate of the target analytes. We've talked about iron. Iron is probably the biggest one to think about. And then in the end, don't forget about the potential role for the aquifer solids in this whole process of evaluating the fate of the aqueous analytes.
I very much enjoyed your presentation, guys. You talked a little bit about one of the things that you suggest doing in addition to what's required in the regulations is something that I guess the regulations forbid. They say you shall not field filter groundwater samples, and some regulators won't even consider those data. But I take it your point is that whether or not the regulations permit field filtering, it should be done anyway to understand what's going on in the aquifer.
That's correct. I mean, there's what's required in the regs, which we're not saying you don't follow the regs, but in addition to, if you want to understand what's going on, there are some other steps you might want to take. Because it can really confound things if there's a lot of suspended sediment. Even that doesn't even take a lot of suspended sediment. Even if your NTUs are in a few tens, you might have enough suspended sediment there that when you're measuring these trace metals at the microgram per liter level, yeah, it becomes important.
Let me ask one more question, just to be a pain.
Yeah.
Because pain is good. I've had regulators tell me they don't really care if the release is coming from the CCR unit or not, if it's caused by the CCR unit. And since the CCR unit interferes with the ability of oxygen to get down to shallow groundwater, essentially can, and I guess in the case of your old CCR unit that had the organic materials, organic rich materials in the berm, it doesn't matter that the release came from the CCR unit, they'll tell me. It only matters that the release was caused by the CCR unit. That seems to me like that's just wrong, but I wonder if you have a reaction to that argument.
Well, yeah, I mean, I agree that it is a wrong argument because it's now the question is, you know, what if you're going to do something about it, where do you look? Yeah, in this case, in that particular example, don't look for the regulated unit. You know, if you're going to if you are required to do something about it, you have to look someplace else. You know, at a minimum, it focuses you on the right direction for a corrective action if you cannot avoid that regulatory outlook.
Yeah, and I'd support that as well. This is not necessarily applications of these techniques are not necessarily restricted to alternate source demonstrations, but they also help you with selection of remedy, right? So if you got to do something and it was caused by the regulated unit, then by understanding these things, it can help you select a remedy that is more likely to be effective, right? So lots of times, if you look at an alternate source demonstration, you might be able to find the ultimate cause of this is natural variability. But if the ultimate cause has something to do with the regulated unit and you have to have a remedy, then it's best to use one that's likely to be effective.
Might that include, for example, getting air down into the aquifer?
It might. Those kinds of it might also involve putting a flow through adsorptive bed that has specific redox characteristics. We've gone the other way when we've been looking at chromate. So you might put up a reducing subsurface barrier, and when groundwater flows through that, it takes the chromium-6 and turns it into chromium-3, which is much less mobile. So there's lots of different things you can do to oxidize or manipulate the redox state of the subsurface that are known to be effective.
Or more appropriately, target a remedy. The same idea, looking at the chemistry with the arsenic, for example, if it is a low ORP setting, maybe the best solution is to use iron and sulfur to start precipitating arsenic iron sulfides. But that would have nothing to do with the actual
unit. Yes,
upgrading
exactly.
unit.
Mm-hmm.
Now you're focusing on what's going on in that downgradient setting, with the unregulated unit.
Thank you.